So as we can see that in single factor ANOVA, there is actually only one variable that is being varied in our analysis. So with this background, let us start applying our understanding to how ANOVA is to be conducted. So the protocol of undertaking ANOVA. So please remember that we still have our original presumptions that there is normality, there is independence of error, and there is equivariance. So these three presumptions still hold for us, and in ANOVA, if we are analyzing I different samples, then we can have, I have made it in a tabular form, that we have samples as 1, 2, 3 up to I, and these samples individually have data points like N1, N2, N3, so on and so forth, and for the ith data set it is Ni. So these individual samples will also have their means, which will be given by the x1 bar, x2 bar, x3 bar, so on and so forth. And since these are samples, they will also have their own standard deviation values, which we denote as S1, S2, S3 and up to Si for the ith sample. And when we square the standard deviation, we get the variance of the data sets. So with these points in our hand, how do we conduct an analysis of variance? So that is shown in the next slide, which you can see now. And what we need to do is, we need to calculate what is known as the grand average, and I will come to it how this needs to be calculated. But for you, it is important to understand that the grand average is actually a weighted average of individual sample means. So this is essentially an average of the whole data set, and in the second step what we do is we obtain the square of deviations between the group means and the grand average. So this will be called as the sum of squares due to factors. Now let us go to the board and understand how these two things can be calculated. That is how grand average and the sum of squares due to factor can be measured or calculated. So going to the board, first let us see how grand average is to be calculated. So we denote the grand average by the symbol x double bar to indicate that it is the grand average, and as we mentioned that x double bar will be a weighted average of the individual means. So it would be N1 by N, where N is the total number of data points that we are dealing with. So we keep doing this. So as you can see that each of these are weighted average, weighted in terms of the number of data points within individual samples. So we calculate the grand average towards the end this would be n ith sample by n into xi bar. So, with this way we calculate our grand average, and the second part was the sum of squares due to factors, which we abbreviate as SSF. So, let us go to the next page and see how the sum of squares due to factors needs to be calculated. So, what we have here is that we say that sum of squares due to factors will be the number of readings in the first sample So, please note that it is a square factor. So, each of the terms will be squared here. And this is essentially the deviation from the grand average, which we denote by x double bar, from the individual sample means. So, we continue this and we get for the ith sample, this will be Ni into xi bar minus x double bar, which is the grand average, and this is how we will be calculating the sum of squares due to factors. So, the sum of squares due to factors considers the square of deviations between the groups. So, please keep this in mind, and for sum of squares due to factors we will have the degrees of freedom as I, which is the number of samples that we are dealing, minus 1. So, for example, if we have 5 different samples, the degrees of freedom would be 5 minus 1 is equal to 4. So, by doing this exercise we will be able to calculate the sum of squares due to factors. Now, let us go back to the desktop and see what we need to do next. Next, we need to obtain what is known as the sum of squares due to variations within the group. So, this is nothing but the error, as we have been discussing in this course, or the fluctuations within a particular sample that we are dealing with. So, this is called as sum of squares due to errors, abbreviated as SSE, and here the degrees of freedom is n, which is the total number of readings, minus I, which is the number of samples that we are dealing with. So, let us look at how the sum of squares due to errors is calculated. So, sum of squares due to errors will be calculated as the summation of deviations in the first group from the mean value of the sample 1 squared, because it is a squared term here, and this continues. So, I then j is equal to 1 to n2 because this is the second sample, and for the third sample similarly we will have x3k minus x3 bar squared, so on and so forth, and finally we will have it for our ith sample. Let us call it y is equal to 1 to ni into summated as iy minus xi bar. So, we calculate the individual deviations or errors in our individual samples and summate the square of it. So, from that we will get the sum of squares due to errors, and as I already mentioned, the degrees of freedom here for sum of squares due to errors is nothing but the total number of readings n minus I, which is the number of samples that we are dealing with. So, let me rewrite this. N is the total number of readings and I are the number of data sets or samples present or being compared. So, we calculate the sum of squares due to errors, then in the next step we calculate the mean square values. So, let us again go back to the desktop, and what we see here is that after we calculate the sum of squares due to factors and sum of square due to errors, we can calculate the mean square factor, which is nothing but the sum of square due to factors divided by the degrees of freedom for the SSF. And in between we have also seen that there is a term which is known as sum of squares due to total, which is essentially the total sum of squares and nothing but the sum of squares due to factors plus the sum of squares due to errors. And since it is a total of all the data set or the data points that we are dealing with, for this the degrees of freedom is nothing but n minus 1, where again n is the total number of data points that we are dealing with. So, it is important to note here that the mean square factor, which we denote or abbreviate as MSF, is an estimate of variance that comes due to the errors within the samples plus the variance between the groups. So, as I have been emphasizing that in analysis of variance we will be comparing these two things, that is the errors within the sample versus the errors between the samples. So, MSF or the mean square factor takes into account both the variances coming from the error plus the variance coming from the between the groups. So, which we have denoted as sigma E square, which is the variance due to errors, plus sigma F square, which is the variance due to the factor under consideration. Now, let us see that how do we calculate the mean square error. It is again very straightforward, that you have the SSE, which is the sum of squares due to errors, divided by the degrees of freedom for the sum of squares due to errors, which is n minus 1. So, As discussed previously, the mean square error, which we abbreviate as MSE, estimates only the variance due to the errors present within a particular sample. That is, it is nothing but the sigma E squared value. Now, when we have MSF and MSE calculated, we will then use these terms to calculate what is our F test value, which is nothing but a ratio of MSF and MSE. And then, as previously, we will be comparing it with a particular critical value of F, which will tell us whether the null hypothesis holds here or not. So, what we have to do after we have performed our ANOVA analysis is to prepare what is known as a ANOVA table, where we summarize our calculations based on the source of variation, which is in the case of factor effect between the groups, and also the variation that is present within a group, which is called as the error effect. And then we, in the next column, we tabulate the sum of squares. So, for the factor effect, this would be sum of squares due to factors, and for the error effect, this will be sum of squares due to errors. And then obviously, when we total both of these, when we add both of these, we get the sum of squares due to total. And as we discussed in the previous slide, that for sum of squares due to factors, the degrees of freedom is nothing but the number of samples minus 1. Similarly, for sum of squares due to errors, it is the total number of measurements minus the total number of sample sets that we are dealing with, that is n minus I. And for the sum of squares due to total, this is simply n minus 1, where n is the total number of data points that we are dealing with. So, based on these, we can calculate the MSF value, the mean square factor value, as well as the mean square error value, and we calculate the F test value as a ratio of the MSF by MSE. So, once we plug in these values, our ANOVA table is ready, and then finally we will compare the F test versus the F critical at 2 degrees of freedom, which will be the I minus 1 and n minus I, and at say 95% or 99% confidence level. So, based on that, we will be able to estimate whether our null hypothesis holds true or not. So, at this point, I would also want to explicitly state what our null hypothesis and alternate hypothesis would be for analysis of variance. So, going back to the board, tell what is the null hypothesis, which is nothing but the population means of the samples being compared are estimated to be or are presumed to be similar. So, if we are dealing with I samples, all of these means are estimated to be similar. Now, it is important to note what the null hypothesis is contrasted to the alternate hypothesis. So, the alternate hypothesis here is that any two or more population means are unequal or different at the confidence level under consideration. So please note that in analysis of variance, we cannot tell precisely which of the 2 or 3 or n number of samples will have the population means different. The alternate hypothesis, which we denote as H1, is nothing but that any 2 or more population means are unequal. What we will do later is to use what is known as the least significance difference to estimate which exact samples are actually different from each other. So that would be part of the exercise for the next lecture, but let us continue with applying ANOVA on a real data set.